What you see here is a simulation of a NAND gate. So here you have the truth table describing the behavior of this circuit. So now the inputs are two switches. So see, if I tap on it, I can switch one input which corresponds to one of these columns here, and this is the other input. I can switch it from 0 to 1. So the switch goes like this. If it's oriented this way, it connects this point to ground, so to 0. Or if it goes like this, it connects the same point to plus 5 volts, which represents our 1. So the moving dots are representing the electric current. So you see what happens if I put both of them at 0, then the pull down network is not activated because the gate voltage is connected to 0. So specifically, the first gate connects this to 0, and then the VDS of this transistor becomes 0, and therefore if the source is 0, also the drain is at 0, and therefore if I put the gate of this transistor to 0, it is 0 respect also to this point, which is 0 because this transistor has a VDS which is 0, and therefore also this one makes its own VDS to be 0, and so this way the current will flow only on those two ones simultaneously, because these are complementary, so these are activated. So the current goes here, it merges with this current, and then it flows at the output. So this is a representation of the output. Here we have a device. It's not a diode, I mean it's a kind of diode, but it's called LED, light emitting diode, like those things here. We will speak about LEDs later. Okay, so if I try to modify the input, now I see what happens. So I have to follow all these things. And one interesting situation is this one. When I activate both of them, both the inputs, the gate voltage is done in a way that basically here I have nothing. So I can try all the possible combination, and the current here, which makes a voltage drop across this load device, will create a voltage corresponding to the values of this truth table. So here is sorry, for the first time an example that shows why the simulators are good for this. This is indeed already a very simple circuit, but still it's getting quite complicated, and it only has 4 transistors. Imagine the others with many transistors. So just to tell you something that might be interesting from an historical point of view, sorry, I want to show you one device I have here, but okay, sorry, first I want to switch to the to this. So nowadays we are full of transistors. I just read on Wikipedia that the ultimate microchip that has been developed for to be used in application of artificial intelligence has a transistor count of 2.6 trillions of transistors in a single microchip. So an enormous amount of transistors, because they are very, very small. They can be done in a size of order of nanometers. So here what I have, it's not a transistor, it's a relay. So this thing is can be easily understood. It's a coil of wire. So the wire is an inductor. So you power up the inductor by giving it electricity to these two connectors here. Then we know that the inductor will produce a magnetic field, and this magnetic field will pull this piece of metal, which is made in iron, so it's magnetic metal, and the magnetic metal with some mechanical levers will move, you see, these little contacts which are switches, and then here you have the contacts of the switches. So this is useful for many things, and they are still useful today. They are called relays. But one interesting thing is that if you have such kind of thing, and I want to go to the blackboard now. Okay. Imagine you have this situation. You have a switch, which is represented by this symbol. Okay. Just a moment. Okay. Then you have another switch like this. Then you can do this. So no, sorry, I want to do another thing. This thing is not interesting at the moment. So let's say you have this thing. This is the inductor. This. So we power up the inductor this way. And the inductor is somehow, with the magnetic field, triggering a lever that makes a switch moving. So like this. So the lever can be arranged in different ways. So for instance, you can make the lever opening or closing a contact according to how you arrange it. So you see that when I push it, one contact is closing, the other one is opening. So if I do something like this, like I connect the battery, so I activate this thing, and the lever will open the circuit here, so-called normally closed switch, which means that without the activation of the magnetic field, this thing is closed. Then this thing can, if I connect it to a source of voltage, and then I put a load like this, then a normally closed switch like this will create a current here only when this thing is deactivated, and if I activate the coil, then this will deactivate the output. So this is an implementation of a NOT gate with simpler electronics which are not involved in transistors, semiconductors like this. So we don't have to think that without semiconductors we can't do digital electronics. In the past, actually, in fact, digital electronics was done with such kind of devices, but look how big they are. So now in a place like this or smaller than this, you can have 2.6 trillions of functional units like this. Okay, so now I want to go back to the presentation. So now that we kind of understood how the story works, we can say that there is also a NOR gate. Also, this time it's a negative logic, but we know the trick. So if you want to have an OR gate, you just put a NOT gate after the NOR gate. And it can be demonstrated that once you have a AND and a NOT, or a OR and a NOT gate, you can create any logic just by combining those elementary circuits together. Let's say something like when you define the multiplication, division, subtraction, I don't know what else in the fundamental operations, then you can do any other calculation. It's just an application of many of these elementary operations. But now we want to be able to implement any truth table. So we want to be able to go from a given truth table to a circuit. We know that there is not only one possible solution, but there can be many. But let's see at least a method to produce one solution. So those circuits are called combinational logic circuits. It means that now we are considering circuits for which the state of the output or the outputs is a function of only the states of the inputs. So what does this mean? It means that there are no so-called feedback connections. So the information propagates from the inputs to the outputs, and you don't see an output connected back to an input in such kind of combinational logic circuits. And also, more precisely, the state of the output, by depending only on the state of the inputs, does not explicitly depend on the time. We will see that there are also other types of circuits which are called sequential circuits, for which the state of the output depends also on the time, and this dependence is due to the fact that there are feedback connections from the output back to the input. But let's start with this. So here we have a truth table. We have a circuit with 3 inputs and 1 output. So here these are just random numbers, can be any. And what we are asking is an output that is 1 only in some cases. So you can think, for instance, of I don't know, these 3 inputs are connected to 3 buttons for an experiment. I mean, the person has to press the buttons, and if the correct let's say pattern is pressed, then the light will be activated, such kind of things. So here we see that if we look at the rows of this table, in this case this pattern at the input is producing a 1. So this pattern is valid for us to make a 1, or this pattern is valid, or this pattern is valid, or this pattern is valid. So whatever between those two, among those four patterns is present, if those patterns are present, one or the other one, it cannot be simultaneously, because you cannot have a value that is simultaneously 0 and 1. But let's say this or this or this or this is good for us to make a 1. So it means that we need to have a sort of OR operation between something in order to make a 1 at the output. And this OR operation is represented by this OR gate. It's an OR gate with 4 inputs. So it's an extension of the OR gate with 2 inputs we have seen so far. So, and what is making this pattern good for us? So we should find a way of building a 1 that goes into each of those 4 inputs of this OR gate out of these 3 inputs. So how can we do this? For instance, let's analyze this case. So if the A input was a 1 instead of a 0, then in order to produce so if it was like this, then it was easy, because we know how to produce a 1 when we have all the inputs to be 1. We just need to put an AND gate with 3 inputs. So this is what we do. We take the A input, we put a NOT gate, so we negate it, and then we put an AND gate with 3 inputs, and this will make the 1 that will be fed into the final OR gate. So this is what is done here. So the A input passes through a NOT gate. So when A, B and C will have a value 0, 1, 1, in a way that here we will have 1, 1, 1, here we will have 1, and this is the 1 that goes in this OR gate corresponding to this input of the OR gate. Similarly for the others. So we can build this circuit this way. So A, B and C are simultaneously applied to all these subunits, and the results is merged into this. So this method is called the min-terms method, and the min-terms are those AND gates. Then there is an interesting thing in electronics, in digital electronics. It is always possible to do one thing and a sort of complementary things. We don't repeat the reasoning, but we can take a shortcut by recalling the DeMorgans law. So if we apply the DeMorgans law to this situation, then we can rewrite the same thing also in this way. We don't do this, but it might be a nice exercise. We just need to apply the DeMorgans laws. So if we can rewrite the output in this different way, it means that here we have another situation. We have the so-called max terms, which are summation. So it means that these are OR gates, and the OR gates then are multiplied together, which means that they go into an AND gate, which is the situation described here. We have an AND gate and several, now 4 subunits built on top of the OR gates. So these two circuits will implement the same result, the same truth table. They are complementary somehow. Okay, so now we have a method, two methods actually, the min terms and the max term, to pass from a given truth table, whatever it is, to a circuit implementing it. So this is a function, formally speaking, of it's like this. Y is a function, binary function of x, where x is a vector input, so it's an input having three entries, A, B, and C. So let's say it has 3 dimensions, but the output has only 1 dimension. We have only one wire at the output. So how can we implement a function that goes from a number of input, let's say equal to n, to a number of output equal to m? It's simple, we just do this. So if we have a circuit that takes a number of inputs, let's say n inputs, and produce, so we have a function, let's call it f1, produces 1 output, then we just replicate this situation. We take another truth table sharing the same inputs like this, and producing a second output, let's call it y1, y2, and so on. Then we have another mth truth table producing an mth output, and this thing is like having a big black box, which is the black box corresponding to all those things collected together, where we have n digital inputs and m digital outputs, and m can also be greater than n, of course. So with digital circuits and truth table we can implement any function from let's say binary n to binary m. So now we are starting doing some mathematics with this. Okay, let's go on. So we already anticipated the idea that there can be circuits whose output depends also on the time. So the first circuit that will show this behavior is something that is useful in order to create so-called oscillators. So let's speak about those oscillators, which is something like this. Now let's go back to the blackboard. So we started this very simple circuit, the NOT gate, and we said that if the input, so let's make the truth table is 0, the output is 1, and if the input is 1, the output is 0. And now I want to do something crazy. I want to connect the output with the input. So while I say something crazy, it's simple, because if this is 0, the circuit will make this 1, but this 1 is connected to this, so then we have this say ugly mathematical thing like 1 equals 0. Is that possible? And of course we have the same problem if we start with a 1. So the gate will produce a 0 according to the circuit, and then this circuit is connecting the 0 here, and then again we have this embarrassing situation where we have 0 equal to 1. So what happens? Will a mysterious force impede us to connect the wire? Will the universe explode if we do this? No, of course not. So this thing is just not captured by this formalism. So it's, from the point of view of the logic, you cannot assemble a circuit like this. But if you try to do this in practice with real transistor, it will work, it will do something. Let's see what it will do. So if we go back, sorry, to slides. So now here I added a couple of components, a resistor and a capacitor, on purpose with some values. So if you notice, the way I connected this is a feedback connection, but I can redraw this circuit like this. So R, C, let's say in and out. So this is a low pass filter where the input is this and the output is that one. So we said that low pass filters, or let's say any filter, come with a transfer function, and the transfer function is a complex number, it's a complex function, and this transfer function has both a magnitude and a phase. And we said that most of the time the magnitude is important, but sometimes the phase is important. This is one of the times where the phase is important. So this circuit does not only create a modification on the amplitude, but also on the phase, which means that will create a delay. So there is a sort of delta tau, delta t, a time that passes from the moment you apply a signal here to the moment you have it at the output. So if we do this, and if we consider, for instance, to have a 1 at the output, so this one corresponds to the fact that here there is a 0. But this one, to appear as a 1 here, will take some time because of this feedback network. So for a moment, this situation will be possible. Then, when this 1 will propagate here and will arrive at this condition, the gate, let's say, immediately will produce a 0 here. But this 0, in order to come here again, will take some time again. So what you have is that this circuit will save the laws of the universe by creating an alternate status at the output and also, of course, at the input. So we have an oscillation like this, from 1 to 0, 1, 0, 1, 0. And the timing of this oscillation depends on the this timing, which ultimately depends on the values of these two resistors and capacitors. So in real life, even if you don't put those components, they are present. They are called so-called parasitic components. So you can't really produce a resistor with an infinite amount of resistance, which means that you can't really disconnect this resistor, so you can't really not having it, and you can't really produce a capacitor with zero capacitance, because the capacitance is the result of two pieces of metal close each other, and even if you put them far each other, they still exist. So they have maybe a little capacitance and the high resistance here. So it might be that these oscillations are very, very rapid, but they are present. So from the point of view of the logic, this is not possible, but in real life, because of this, there we will have an oscillator. And we will make use of this oscillator as a sort of clock that will be used in a circuit that we will study in a while, which are called sequential logic circuits. So circuits whose status depends also on the time.